Here the system given to you is a rectangular shape, or you can say one side is a square shape 1 centimeter by 1 centimeter, and the other side, if you see, is a rectangular shape 1 centimeter by 15 centimeter. So a rectangular carbon block has been given to you, which has a dimension of 1 centimeter into cross 1 centimeter cross 50 centimeter. Resistance are measured first across the two square sides, two square ends, and then across the two rectangular ends, respectively. If the resistivity of the carbon material, that is given to be 3.5 into 10 raised to power minus 5 ohm meters, then the value of measured resistances respectively are. So basically you know how to correlate the resistance with the resistivity, right? You know the formula. You have studied the formula in the theory sessions. But there is one important catch in the formula. That catch I'll discuss with the help of this problem. Okay, now let's move on to the system. So when you are set to measure the resistance between the two square sides, or like two square areas, that means you are connecting the battery like this. These are the two square areas, right? So if you connect the battery like this, in order to measure the resistance across this end and this end, you have to connect the battery. So if you connect the battery, the current will flow from this area to this area like this, correct? And you know the formula for resistance and resistivity. The correlation is given as R, that is the resistance is given as rho times L by A. It is very important formula, fundamental formula. Just the criticality is you have to understand the meaning of L and A. They change as per the orientation of the system, as per the orientation of the current flow. So when I say length is the length measured across the current flow, along the current flow. And when I say area is perpendicular cross-sectional area to the current flow. So like the current is flowing, let's say like this, then the area should be measured like this. The cross-sectional area should be like this, which is perpendicular to the, or like the surface should be perpendicular to the flow. That area you have to take, right? So based upon the measurement or based upon the orientation, your values of L and A for this formula changes, right? It's not like that the system is given to you, so the length will be 50 centimeter and the area will be 1 centimeter square. No. Length and area, they are measured with respect to the orientation, with respect to the current flow. Length along the current flow, the cross-sectional area perpendicular to the current flow. Correct. So when you are having a system like this, when you are attaching the batteries from the two square surfaces, please understand this. The length will be 50 centimeter, right? And the cross-sectional area will be this area, which is 1 centimeter square, correct? So in that case, R across the square terminals, I can say, is equal to rho times, rho that is 3.5 into 10 raised to power minus 5 times L. What is the length? Length is 50 centimeter, that's 50 into 10 raised to power minus 2 meters, divided by cross-sectional area, that's 1 centimeter square, right? This area is perpendicular, right? This area, if you see, this area is perpendicular, right? Perpendicular to the flow of current, right? So that's 1 centimeter square. So 1 centimeter square is nothing but 10 raised to power minus 4 meter square. Correct? This, if you solve, please understand this. 10 raised to power minus 4 will go up, make it 10 raised to power 10 raised to power plus 2. Plus 2 multiplied by minus 5 will make it 10 raised to power minus 3. So it becomes 3.5 into 50 into 10 raised to power minus 3. And it is resistance, so it's ohm. Correct? Now, this comes out to be, please understand this comes out to be 3.5 multiplied by 5 multiplied by 10 raised to power minus 2 ohms. This comes out to be 35 divided by 2 multiplied by 10 raised to power minus 2 ohms. That's your first answer. That's your first answer when you attach or when you measure the resistance across the square surfaces. But the second scenario is when you are measuring the resistance of the same system but not across the square surfaces, across the rectangular ones. Say for example this one and this one. When you attach the battery like this, please understand there's something which is going to change. What is going to change? The direction of current flow. So the direction of current flow will be from one square surface to the other square surface where the other terminal of the battery is being connected. Correct? So the length in this case will be the length of this, which is 1 centimeter. right? Length along the current flow. And the cross-sectional area will be the area perpendicular to the current flow, like this. You see this? So the cross-sectional area in the second case, when you are connecting the battery from the rectangular surfaces, the cross-sectional area this time will be 50 centimeter multiplied by 1 centimeter. That's 50 centimeter square. So across the let's just write over there r across the rectangular surfaces. That is equal to rho multiplied by length. Please tell me what is the length. Length is 1 centimeter. That's 10 raised to the power minus 2 meters. Divided by cross sectional area is 50 centimeter multiplied by 1 centimeter. That is 50 centimeter square. That's 50 into 10 raised to power minus 4. And the value of rho you just have to put it. So the value of rho, let's just do this. Value of rho is 3.5 into 10 raised to power minus 5 multiplied by 10 raised to power minus 2 divided by 50 into 10 raised to power minus 4. Now you solve this. So when you solve this, this becomes minus 4, this becomes plus 4 on the upper side, this becomes 10 raised to power minus 1 minus 2, that's 10 raised to power minus 3, right? So it becomes r across rectangular surfaces becomes equal to 3.5 multiplied by 10 raised to power minus 3 divided by 50. Correct? This becomes equal to 35 by 50 into 10 raised to power minus 4. Correct? This becomes 7 into 10 raised to power minus 5 ohms. Correct? So the answer here in the second case will be 7 into 10 raised to power minus 5 ohms, right? So depending upon the orientation, your resistance of the system is changing. Why? Because the length across the current flow and the cross-sectional area for the current, that is changing for the system, right? So in this case, the answer will be option A. The first case, 35 by 2 into 10 raised to power minus 2 ohms. And the second case, it's 7 into 10 raised to power minus 5 ohms. Here the statement is, all the edges of a block with parallel faces. Parallel faces means the opposite faces are parallel. So the opposite faces are parallel and the edges are unequal. That means the side lengths are unequal but the opposite faces are parallel. Correct? Now the statement says its longest edge is twice of its shortest edge. That means if you look into the figure given, there are three sides A, B and C. And from the figure you can get this intuition that B is the longest and C is the shortest. And you can see the opposite faces are again parallel as said in the problem. Correct? Problem statement. Now it says B is equal to 2C. The longest is twice of the shortest. B is equal to 2C, equation 1. From the given question statement as well, right? Okay, now it says what is the maximum to minimum resistance between parallel phases? So say for example, you connect this material across a battery across the parallel phases, right? So what is the maximum resistance you can get and what is the minimum resistance you can get? You have to take the ratio of both of them, right? Okay, maximum to minimum resistance ratio. So let's talk about this. So the first and foremost thing is B is equal to 2 times C. B is the longest side and C is the shortest side, right? And A is in between. There are three phases, right? Three sides, right? A, B, C, three edges. A, B and C. Now, please understand this. When you write R is equal to rho L by A, what is rho? Resistivity of the material. Now, material is a fixed thing in this problem, right? You're not changing the material. You're just changing the orientation, right? Across different set of phases, you are talking about the resistances, right? So the rho in any case is going to be constant in this case. What is L? L is the length across the current flow and A is the area, cross-sectional area perpendicular to the current flow, right? So please understand this. For that matter, if you connect this with a battery like this, so if you connect these two phases, one is this phase and the second is this phase. Is this a set of parallel phase? Yes. So the current will flow like this into the material, right? So if you talk about the length across the current flow, that comes out to be C. And if you talk about the area, cross-sectional area, that comes out to be this perpendicular area. That comes out to be this, right? This cross-section, right? So the cross-sectional area comes out to be AB. Am I okay with that? Yes. Okay, so in order to maximize the resistance, you have to maximize the length and minimize the cross-sectional area, right? And in order to minimize the resistance, you have to minimize the length, because R is equal to rho times L. So it is directly proportional to L, right? So you have to minimize the length. You have to take such an orientation where the length is minimum and the area is maximum, right? Because R is inversely proportional to A, correct? Now we will talk about the different possible configurations in this case. So what are the different possible configurations, right? There are three possible configurations. One, you attach like this, the battery. One, you attach like this, the battery. And one, you attach like this between these two phases, right? Correct? Correct? Okay. Now, if you want to maximize the resistance, let's say we talk about the maximum resistance, that is equal to rho times what is the maximum length possible. So the maximum length possible is across B, correct? If you go like this, then the length will be maximum, right? So the maximum length possible is B divided by what is the cross-sectional area in this case? The cross-sectional area in this case is this cross-sectional area, right? Because the current is flowing like this, correct? So the cross-sectional area is this. That by default becomes the minimum cross-sectional area possible. How? Because it's A multiplied by C. Cross-sectional area is A multiplied by C. C is the smallest side and A is the side which is in between. So of course AC is the minimum cross-sectional area possible, correct? So if you take the length as B, the cross-sectional area by default becomes minimum, that is AC, correct? So R max will be given as rho times what is B? B is 2C divided by AC. That becomes 2 rho by A, equation 1. And if we talk about now about the R minimum is equal to rho times what is the minimum length possible? The minimum length possible is across C, correct? When you connect the battery like this, the R will be R minimum, correct? How? Because the length is becoming minimized, that is C divided by what is the cross-sectional area in this case? The cross-sectional area we already talked about in this case will be A times B, where B is the longest side and A is in between. So AB is the maximum cross-sectional area possible, right? So the cross-sectional area AB is maximized, and in that case it becomes rho C by A into 2C. That becomes rho by 2A. That is equation number 2. If you take the ratio R max to R min, that becomes 2 rho by A divided by rho by 2A, correct? Correct? Rho cancels, correct? A cancels, and this 2 multiplies that upper 2, that becomes 4. So the answer here in this case will be R max divided by R min is equal to 4. Option B in this case will be the correct option. Here this problem is being given from an important concept. Based on this concept or based upon this logic, problems have been asked multiple times in your examination. Multiple times I'm saying, in various examinations. So please focus once and for all, right? So if you understood this here, then problems based on the simple logic like this will always be easy for you. But let's grab the concept over there. So the statement says the length of a given cylindrical wire is increased by 100%. That means you are stretching it. Length is increased, that means you are stretching the wire such that if initial length was L, the final length is a 100% increased length. That is 2L, right? Due to the consequent, there is decrease in diameter. Due to this stretching, basically the diameter decreases. The change in the resistance of the wire will be. So basically the resistance is also changing because it depends on the length and the cross-sectional area, correct? So what I say, the question is given like this. So initially, let's say you have a diameter D and a length L. Length L of the cylindrical wire. That means if you start moving from there along the wire like this, then this total length is L. This total length from A to B. This is L, correct? So when the current is moving like this, basically how much it travels? L. And the diameter is given to be D. When it is stretched, when the wire is stretched, basically the diameter changes to D dash and the length changes to 2L because there's a 100% increase, correct? A comes here, B comes here, and the distance between them becomes 2L, correct? And you know the formula for resistance is always given as rho L by A, where L is the length across the current flow and A is the cross-sectional area perpendicular to the current flow, correct? Now in the first case, let's say what is constant? In the two cases, what is constant? It's the volume. It's the same wire which is being stretched, right? So the volume will remain constant. The length will change, the cross-sectional area will change, the diameter will change, but the volume of the material in the wire, that will be constant, right? So in the first case, volume initial will be L times pi d square by 4. And in the second case, the final volume will be 2L times pi d dash square by 4. When you keep them equal, when you put them equal, the volume initial is equal to volume final, what you get, Vi is equal to Vf. What you get d square is equal to 2d dash square, right? So the initial cross-sectional area was basically, let's say A, was basically how much? Pi d square by 4. And the final cross-sectional area was, let's say pi d dash square by 4. Now d dash square you can write as d square by 2. D dash square you can write as d square by 2. So it becomes pi d square by 4 multiplied by 1 by 2. That is A by 2. So if the length is being 2 times, the cross-sectional area is reduced to half of its value, correct? That's how you can figure it out. You can directly get that from A initial into L initial is equal to A final into L final without involving the diameter itself, right? You can get this relation. That if length is twice, then the cross-sectional area should be half of the initial value, correct? In order to keep the volume constant, correct? In this case, R initial will be equal to rho into L initial by A initial. That is rho L by A. And R final will be rho into L final by A final. That is equal to rho times, what is L final? That is 2 times L. And what is A final? Final cross-sectional area, that is A by 2. So that's 4 rho L by A. That if you look into, that becomes 4 times R initial. So R final is 4 times R initial. So what is the increment? The increment delta R is R final minus R initial. That is equal to 3 times R initial. That means R initial now has become 4 times R initial. So what is the increment? 3 times R initial. So the percentage increment will be 300%, right? So in this case, the answer will be option A, 300% increment in the resistance, in the value of the resistance of the system. Here the statement is, the potential difference across a wire of cross-sectional area 10 raised to power minus 3 centimeter square and 50 centimeter length is 2 volt. The battery you are applying across the wire, that is given to be 2 volt, right? And the current from the wire is 0.25 ampere. That is given to you. And the length of the wire is 50 centimeter and the cross-sectional area is 10 raised to power minus 3 centimeter square. Now it says the conductivity of the material is given by. So the conductivity, as you all know, is defined as 1 upon resistivity. You know that, right? Conductivity is 1 upon resistivity, correct? Now, if we take this problem, we know that V is given as IR, correct? Voltage difference applied is equal to current multiplied by resistance. And the resistance you already know is given as rho L by A, correct? Resistivity multiplied by length divided by cross-sectional area, correct? And you just have agreed that rho is 1 upon sigma, correct? Where sigma is the conductivity, rho is the resistivity. So this can be written as I into L upon sigma A, right? So basically what I say is this, V is equal to I times L upon sigma A. Now in this scenario, you know everything apart from sigma. So if you write V is equal to IL by sigma A, sigma comes out to be IL by VA. What is I? I is the current, that is given to be 0.25 into 0.25 ampere, right? L, what is L? 50 centimeter, that is 50 into 10 raised to power minus 2 meter, divided by voltage difference applied, that is 2 volt, multiplied by cross sectional area. What is the cross sectional area given to you? 10 raised to power minus 3 centimeter square. So please keep in mind, you have to take care of the units. So 10 raised to power minus 3 centimeter square is 10 raised to power minus 3 multiplied by 10 raised to power minus 4 meter square. I just converted it into meter square, correct? Now if you solve this, what you get is this. Sigma is equal to 6.25 into 10 raised to power 5 ohm inverse meter inverse. So basically this MHO is ohm inverse. How you write it? You see this. What was R? R was rho L by A. And rho you can write as 1 upon sigma. So it becomes L upon sigma A. Correct? So sigma becomes basically L upon, I'm just talking about the units, L upon R into A. A is meter square and L is meter. So if you talk in terms of the units, then sigma's unit should be 1 upon R, 1 upon the unit of R multiplied by multiplied by meter, because this is meter and this is meter square. So this will cancel this, right? So the unit of sigma should be 1 upon ohm meter. And 1 upon ohm inverse is written in terms of MHO, right? Okay, you can call this as mho. But yeah, it's ohm inverse. So the answer in this case is 6.25 into 10 raised to power 5 ohm inverse meter inverse. Let's look into the options. Option B in this case will be the correct option. Here the problem is very simple, but you have to apply a little bit of mathematical interpretation, the graphical knowledge of yours in this problem, and the problem is done. So the statement says the current in a metallic conductor is plotted against the voltage at two different temperatures T1 and T2. The metallic, keep in mind, the metallic conductor which is being taken, that is same. What is the difference? The temperature is different. In one case, the metallic conductor is at a temperature T1. In the other case, the metallic conductor is at a temperature T2. And in the two cases, we apply a voltage and we measure the current. Then we change the voltage and we vary the current. And we plot I versus V graph, right? And the graphs are given to you. Which of the following options is correct based upon the graph which is given to you? So what is the graph? This is the graph given to you. I versus V graph at two different temperatures, correct? Okay, very easy. How to compare T1 and T2? T1 is the temperature in the first case, T2 is the temperature in the second case. Please understand this. I versus V is a straight line. That's okay. That's okay. Agreeable. So you know this formula, V is equal to IR across a metallic conductor, right? Across a conductor, right? Ohm's law, correct? Okay, you have to plot I versus V graph, right? So you have to put I on the y-axis and V on the x-axis. So I would like to write this function, this formula, in terms of y is equal to mx. Y that is on I-axis is equal to V that is on x-axis divided by R. This is on y-axis and this is on x-axis. In general, the equation of a straight line in xy plane is given as y is equal to mx, which is passing through origin, of course. Otherwise, there is a constant added, mx plus c. Correct. But it is passing through a straight line, so y is equal to mx kind of graph is given to you, where m is the slope. And m geometrically is given by the value of tan theta. You know that, right? Where theta is the angle made by the line from the positive x-axis, correct? Okay, nice. In this case, if you equate this y is equal to mx, then m comes out to be 1 by r. Right? And m is tan theta, so tan theta is 1 by r. So you can say resistance is equal to 1 by tan theta for the graphs. That means for the graph or for the line for which the tan theta is more, the resistance will be less. For which the tan theta is more, the resistance will be less. Because if you compare y is equal to mx, taking I on the y-axis and v on the x-axis, you get m, that is slope, that is tan theta, as 1 by r. So from there you got r is equal to 1 by tan theta. That means more the value of tan theta, less the value of r. Now in the two cases where theta is more, in between 0 to 90, more the theta, that means more the tan theta. Correct? So we know that tan theta 1 is of course greater than tan theta 2 because theta 1 is greater than theta 2. So if tan theta 1 is greater, that means r in the first case is less than r in the second case. Right? Now for a metal, if you increase the temperature, the resistance increases. So more the temperature, more should be the resistance. R2 is more, that means the temperature of the metal, of the metallic conductor corresponding to the resistance R2 should be more. More the temperature, more will be the resistance. In what case? In the case of metals, not in the case of semiconductors. There's a different logic, right? In the semiconductors, you have studied in theory. There is some difference, right? But for the metals, more the temperature, more will be the resistance. More will be the electrical resistance. Correct? So R2 is more than R1. That means T2 is also more than T1. Temperature in the second case is also more than temperature in the first case. That means T1 should be less than T2. So the correct answer in this case will be T1 less than T2. Now let's look into the options. Option B in this case will be the correct option.